Welcome to a moment of stillness. In the rush of our daily lives, we rarely pause to look up. But tonight, imagine yourself standing beneath an open sky, far from city lights, where the darkness is complete and the stars emerge one by one. Thousands of them. Millions, more than you could ever count. This is infinite science. And tonight, we invite you to step away from the familiar world and drift outward into the vast, silent ocean of space and time. What you're about to experience isn't just a collection of facts. It's a journey through the deepest mysteries our species has ever encountered. Questions that have haunted humanity since we first gained the ability to wonder. Questions about where we came from, what lies beyond the edge of everything we know, and whether we're truly alone in this incomprehensible expanse. The universe is not loud. It doesn't demand your attention. It simply exists, patient, ancient, indifferent to whether we understand it or not. And yet, here we are. Conscious beings made of star matter, standing on a tiny world, peering into infinity and daring to ask, why? Tonight, we're going to explore the strangest, most humbling truths about reality itself. We'll journey back to before time began. We'll watch the first stars ignite in an ocean of darkness. We'll discover how black holes warp the very fabric of existence, and we'll confront the unsettling fact that most of the universe is invisible, made of something we cannot see, cannot touch, and barely understand. But we won't rush. There's no urgency here. The universe has been unfolding for 13.8 billion years. It can wait a little longer while we try to comprehend even a fragment of its beauty. So take a breath. Let the noise of the world fall away, and join us as we drift into the infinite. The stars are waiting. Before we journey to the beginning of time, before we explore black holes and distant galaxies, let's start with something simpler, something closer to home. Let's talk about perspective. Right now, as you experience this moment, you're sitting or standing on the surface of a planet, Earth. A rocky sphere about 8,000 miles in diameter, spinning on its axis once every 24 hours, orbiting a star we call the Sun. This seems obvious, mundane even. But think about what it means. You're on a sphere, a ball of rock and metal hanging in space. There's no up or down in any absolute sense. The only reason you don't fall off is gravity, the planet's mass pulling you toward its center. People on the other side of the world are literally upside down relative to you, yet they feel perfectly right side up. This realization that Earth is a sphere floating in space took humanity thousands of years to fully accept. Our ancestors looked at the horizon and saw flatness. They felt the ground beneath their feet and assumed it extended infinitely in all directions, with the sky as a dome overhead. But it doesn't. Earth is finite. Walk far enough in any direction and you'll return to where you started. The horizon you see is simply the curve of the planet blocking your view of what lies beyond. Now, zoom out. Earth orbits the Sun at a distance of about 93 million miles. That distance from Earth to the Sun is called an astronomical unit. 1 astronomical unit. It takes light about 8 minutes to travel this distance. When you see the Sun in the sky, you're seeing it as it was 8 minutes ago. The Sun itself is a medium-sized star, a glowing ball of plasma about 865,000 miles in diameter. You could fit over 1 million Earths inside it. It's so massive that it contains 99.86% of all the mass in the solar system. Everything else, all the planets, moons, asteroids, comets, is just leftover debris from its formation. And our solar system extends far beyond the planets we learn about in school. Beyond Neptune lies the Kuiper Belt, a region of icy objects where Pluto resides. Beyond that is the scattered disk, and farther still, the Oort cloud, a vast spherical shell of comets extending perhaps halfway to the nearest star. The Oort cloud might extend as far as 1 light-year from the Sun. That's the distance light travels in an entire year, about 6 trillion miles. And that's still within our solar system. Now zoom out again. The nearest star to our Sun is Proxima Centauri, about 4.2 light-years away. If you could travel at the speed of the fastest spacecraft humans have ever built, Voyager 1, moving at about 38,000 miles per hour, it would take you about 70,000 years to reach Proxima Centauri. We haven't left our solar system yet. Voyager 1, launched in 1977, only crossed into interstellar space in 2012. It's been traveling for nearly 50 years and has barely left the neighborhood. The galaxy contains between 200 and 400 billion stars. Some are larger than the Sun, some smaller. Some burn bright and fast, others dim and slow. And most of them probably have planets, billions of worlds, scattered across the spiral arms of the Milky Way. The Milky Way itself is about 100,000 light-years across. It takes our solar system about 225 million years to complete one orbit around the galactic center. The last time we were in this position in our orbit, dinosaurs were just beginning to emerge on Earth, and the Milky Way is just one galaxy among trillions. The observable universe extends about 46.5 billion light-years in every direction from Earth. Not because the universe is 93 billion light-years old, but because space itself has been expanding since the Big Bang. The light we see from the most distant galaxies has been stretched by that expansion. Within the observable universe, we estimate there are somewhere between 100 billion and 2 trillion galaxies, each containing billions or trillions of stars. The numbers become meaningless. The mind cannot hold them. And yet, this is where we are. This is the context of your existence. You are sitting on a planet, orbiting a star, in a galaxy, in a universe so vast that light from its farthest reaches has been traveling for over 13 billion years and still hasn't reached us yet. Every person you've ever known, every story ever told, every empire that has risen and fallen, every work of art, every scientific discovery, every moment of joy and sorrow in human history, all of it has happened on this one small world. Carl Sagan called Earth a pale blue dot after the Voyager 1 spacecraft took a photograph of our planet from the edge of the solar system. In that image, Earth is less than a pixel in size, a tiny speck of light suspended in a sunbeam. Look at that dot. That's here, that's home, that's us. This is the cosmic perspective, the realization that we are incredibly small, that our lives are brief, that our concerns, as important as they feel, are happening on a stage almost invisible in the cosmic arena. And yet, despite our smallness, we matter. Not because the universe cares about us. It doesn't. It can't. But because we care. Because we're conscious. Because we can look up at the night sky and understand what we're seeing. We know we're on a planet. We know that planet orbits a star. We know that star is one of billions in a galaxy. We know that galaxy is one of trillions in an expanding universe. We've figured this out. Tiny creatures on a tiny world, and we've mapped the cosmos. This is extraordinary. This is what makes the cosmic perspective both humbling and empowering. We are small, yes, but we are not insignificant. We are the universe's way of knowing itself. And now that you have this perspective, now that you've zoomed out and seen where we are in the grand scheme of things, we can begin our journey properly. We can go to the beginning, to the moment when space and time themselves came into existence, to the Big Bang. Are you ready? Let's go deeper. Let's begin at the beginning. Except there is no beginning, not in the way we understand it. Imagine trying to point to the edge of a sphere. You can't. There is no edge. Now imagine trying to point to the moment before time itself existed. It's impossible. Not because we lack the instruments or the mathematics, but because before is a concept that requires time. And time, as far as we can tell, began with the universe itself. This is where science meets the limits of human intuition. This is where even our language begins to break down. 13.8 billion years ago, everything that exists, all the matter, all the energy, all the space itself, erupted into being from an unimaginably hot, dense state we call the Big Bang. Not an explosion in space, but an explosion of space. The universe wasn't born into a pre-existing void. The void itself was born. In that first fraction of a second, a trillionth of a second, the universe expanded faster than the speed of light. This period, called cosmic inflation, stretched space itself, smoothing out any irregularities and setting the initial conditions for everything that would follow. Galaxies, stars, planets, you. But here's the mystery that keeps cosmologists awake at night. What caused it? We can trace the universe's history back to that first instant, but we cannot peer beyond it. The mathematics of general relativity break down at the singularity, the point of infinite density where all the rules collapse. It's as if the universe has drawn a curtain across its own origins, leaving us to wonder what, if anything, existed before. Some theorists propose that our universe emerged from a quantum fluctuation, a random blip in a pre-existing quantum field. Others suggest it budded off from a parent universe in an eternal process of cosmic reproduction. Still others argue that time itself might be cyclical, that our Big Bang was actually a big bounce, the latest iteration in an endless series of expanding and contracting universes. But these are speculations, educated guesses. The truth is, we don't know. And perhaps we never will. Because to ask what came before the Big Bang might be like asking what's north of the North Pole. The question itself may not make sense. Time, as we experience it, may have no meaning at that scale. Cause and effect, the fundamental logic we use to make sense of reality, might simply not apply. This is humbling. We are creatures who crave explanations, who need to fit everything into a narrative with a clear beginning, middle, and end. But the universe doesn't owe us a story we can understand. It simply is. And yet, despite our limitations, we've managed to piece together a remarkable picture of what happened after that first instant. We've detected the faint afterglow of the Big Bang, the cosmic microwave background radiation, a whisper of light from the earliest moments of time, still washing over us from every direction. We've measured the universe's expansion, watched galaxies racing away from each other, and calculated backward to that singular moment of creation. We stand here, 13.8 billion years later, asking questions the universe itself cannot answer. And in that act of questioning, in that refusal to accept mystery without investigation, we touch something profound about what it means to be human. We are the universe trying to understand itself. And our journey has only just begun. For a long time, there was only darkness. After the initial burst of creation, after the universe had expanded and cooled enough for the first atoms to form, space entered what cosmologists call the Dark Ages. This period lasted for hundreds of millions of years. An eternity by human standards, barely a moment in cosmic time. During this epoch, the universe was filled with neutral hydrogen gas. No stars, no galaxies, just a vast cooling fog drifting through the darkness, waiting for something to happen. The temperature of this primordial gas was dropping. In the immediate aftermath of the Big Bang, the universe was so hot that matter existed only as a plasma, a soup of free electrons and atomic nuclei, too energetic to form stable atoms. But as space expanded, it cooled. And about 380,000 years after the Big Bang, something remarkable occurred. The universe became transparent. For the first time, electrons and protons combined to form neutral hydrogen atoms. This process, called recombination, meant that light could suddenly travel freely through space without being scattered by free electrons. The universe went from opaque to clear, and the cosmic microwave background radiation was released. That faint glow we can still detect today, the oldest light in existence. But there were still no stars. Not yet. Gravity, however, was patient. It worked slowly, pulling hydrogen gas into denser and denser clumps. Over tens of millions of years, these clumps grew larger. As they contracted, they heated up. Pressure built in their cores. And then, somewhere in the darkness, something ignited. The first star. We don't know exactly when it happened. We haven't yet directly observed these primordial stars, though the James Webb Space Telescope is actively searching for them. But we know they must have existed because everything that came after depends on them. These first stars were nothing like our sun. They were massive, perhaps 100 times more massive, and burned with fierce, blue-white intensity. They were made purely of hydrogen and helium, the only elements that existed at the time. No carbon, no oxygen, no iron. The universe was still chemically simple, almost primitive. But these stars, called Population 3 stars, were crucibles of creation. In their cores, nuclear fusion transformed hydrogen into helium, releasing tremendous energy. This energy created radiation pressure that fought against gravity, achieving a delicate balance that allowed the stars to shine steadily for millions of years. But fusion didn't stop at helium. As these massive stars aged, they fused helium into carbon, carbon into oxygen, oxygen into neon, silicon, and eventually iron. Each step released energy. Each step created heavier elements. The universe was learning chemistry. And then, inevitably, these giants died. When a massive star exhausts its fuel, there's nothing left to hold it up against its own gravity. The core collapses in a fraction of a second, and the outer layers rebound in a catastrophic explosion, a supernova. For a brief moment, a single dying star can outshine an entire galaxy. In that violent death, something beautiful happened. The explosion forged even heavier elements, gold, silver, uranium, and scattered them into space. The pristine hydrogen gas of the early universe was now seeded with the raw materials for planets, for oceans, for life. The first light wasn't just illumination, it was transformation. These early supernovae rippled through the surrounding gas, triggering new waves of star formation. Slowly, over hundreds of millions of years, the universe lit up. Islands of light appeared in the darkness. Clusters of stars formed. The first galaxies began to take shape. And in time, in one of those galaxies, orbiting one of those later generation stars enriched with the ashes of ancient supernovae, a planet would form. And on that planet, conscious beings would eventually look up at the night sky and wonder about the light they saw. That planet is Earth. Those beings are us. Every atom in your body heavier than hydrogen was forged in the core of a star that died billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you breathe. All of it was created by fusion and scattered by supernovae. You are not separate from the universe. You are not an observer standing outside it, looking in. You are made of the same substance as the stars. You are the universe experiencing itself, thinking about itself, marveling at its own existence. This is not metaphor. This is literal truth. Consider this. The iron in your blood was forged in a supernova explosion billions of years ago. That iron atom has journeyed across space and time to become part of you. It drifted through interstellar clouds, became part of the molecular cloud that formed our solar system, was incorporated into the early Earth, cycled through countless geological processes, was taken up by plants, eaten by animals, and eventually became part of your hemoglobin, carrying oxygen through your veins. That single atom has witnessed the evolution of the cosmos. It has seen stars born and die. It has traveled light years through the void. And now, it's part of you, enabling you to think, to move, to live. Every atom in your body has a similar story. Some are ancient, hydrogen from the Big Bang itself. Others are younger, carbon created in stellar cores only a few billion years ago. But all of them were forged in cosmic fires, scattered by stellar winds and supernovae, gathered by gravity into new structures. You are a temporary arrangement of ancient materials, a brief pattern in the endless cycling of matter through the universe. And yet, while this pattern exists while you exist, you have the extraordinary privilege of being able to contemplate your own origins. The first light didn't just illuminate the cosmos, it created the possibility of everything that would follow, including you. Including this moment, right now, as you contemplate the journey that light has taken to reach your eyes. Those early stars, Population 3 giants burning in the cosmic darkness, knew nothing of what they were creating. They had no awareness that their deaths would seed the universe with the building blocks of planets and life. They simply burned according to the laws of physics, fused elements in their cores, and exploded when their fuel ran out. But from those deaths came possibility. From destruction came creation. The ashes of the first stars became the raw materials for everything that followed. Second-generation stars, then third, then fourth. Each generation enriching the universe with heavier elements, making more complex chemistry possible. By the time our sun formed 4.5 billion years ago, the universe had been preparing for billions of years. The carbon, nitrogen, oxygen, phosphorus, sulfur, all the elements essential for life, were available in abundance, forged in countless stellar furnaces and scattered by countless supernovae. Life on Earth was only possible because of this long cosmic history, because stars lived and died, because supernovae scattered their ashes, because gravity gathered those ashes into new stars and planets, because one particular planet at one particular distance from one particular star had the right conditions for chemistry to become biology. We are not just made of star stuff. We are the universe's way of reflecting on its own history. We are matter that has become complex enough to ask where it came from. We are all children of the first stars, and their light still shines within us, not just as inspiration, but as literal physical reality. The photons from those ancient supernovae are gone, absorbed and scattered long ago, but their legacy remains, written into every cell of your body. If you could live for billions of years and watch the sky in time-lapse, you would see that stars are not eternal. They are born, they live, and they die. Each one follows a path determined by its mass. A cosmic script written in the laws of physics. Let's follow the life of a star from birth to death and understand why mass is destiny in the stellar world. Stars are born in stellar nurseries, vast clouds of gas and dust called molecular clouds. These clouds can be hundreds of light years across, containing enough material to form thousands of stars. The most famous of these nurseries is the Eagle Nebula, home to the iconic Pillars of Creation photographed by the Hubble Space Telescope and later by the James Webb Space Telescope in stunning infrared detail. These pillars are structures of dense gas and dust sculpted by the radiation from nearby hot, young stars. Within them, new stars are forming even now, hidden from visible light, but revealed by infrared observations. The pillars are slowly being eroded by the intense ultraviolet radiation, but they'll continue birthing stars for millions of years to come. Something disturbs the cloud. Perhaps a nearby supernova, perhaps the shock wave from another star's death, perhaps the gravitational influence of a passing gas cloud. The disturbance creates ripples in the gas, and gravity takes hold. The cloud begins to collapse in on itself, fragmenting into smaller clumps. Each clump contracts, heating up as gravitational potential energy converts to thermal energy. This contraction takes time. For a solar mass star, the collapse from a diffuse cloud to a protostar takes about 100,000 years, which seems long by human standards but is remarkably quick on cosmic timescales. The cloud is falling in on itself at supersonic speeds, and as it contracts, it heats up. At the center of one of these clumps, temperature and pressure rise. For tens of thousands of years, the protostar grows, pulling in more and more material. It begins to spin, because any rotation in the original cloud is conserved and amplified as it contracts, like an ice skater pulling in their arms. A disk of gas and dust forms around it, the birthplace of future planets. The protostar is now generating heat from gravitational contraction, glowing in the infrared. But it's not yet a true star, not yet sustaining itself through nuclear fusion. It's still in the process of collapsing, still gathering mass, still heating up. And then, when the core temperature reaches 10 million degrees Celsius, something extraordinary happens. Hydrogen nuclei, normally repelled by their positive charges, are moving so fast and pressed so close together that they overcome that repulsion and fuse. Two hydrogen atoms become one helium atom. In the process, a tiny amount of mass, about 0.7%, is converted to energy according to Einstein's famous equation, E equals mc squared. This doesn't sound like much, but consider. That equation says that mass and energy are equivalent, and the speed of light squared is an enormous number. A tiny amount of mass converts to a tremendous amount of energy. The star ignites. This is the moment of birth. Radiation pressure from the fusion reactions pushes outward, balancing gravity's inward pull. The star has achieved hydrostatic equilibrium. It will remain in this stable state, what astronomers call the main sequence, for most of its life. How long that life lasts depends entirely on mass. And here's the counterintuitive part. More massive stars live shorter lives, not longer ones. Why? Because massive stars don't just have more fuel, they also burn it much faster. A star 10 times the mass of the Sun doesn't live 10 times longer. It lives about 20 times shorter. The relationship isn't linear. It's much steeper than that. Massive stars burn hot and fast. A star 50 times the mass of our Sun might live for only a few million years. A cosmic eye blink. Its core temperature is so high, its fusion rate so fast, that it races through its hydrogen fuel like a bonfire, consuming dry wood. It shines brilliantly, hundreds of thousands of times brighter than our Sun. But it lives recklessly and dies young. Our Sun, a medium-sized yellow dwarf, is more prudent. It has been burning steadily for 4.6 billion years and will continue for another 5 billion. It's middle-aged now, about halfway through its main sequence lifetime. It burns its hydrogen at a controlled rate, converting about 4 million tons of mass into energy every second. That sounds like a lot, but the Sun is massive enough that it can sustain this for billions of years. Small red dwarf stars, the most common type in the universe, are incredibly frugal. They have lower core temperatures, so their fusion rates are slow. They can last for trillions of years. In fact, red dwarfs born in the early universe are still on their main sequence today. Not a single red dwarf has ever died of old age. The universe isn't old enough yet. The smallest red dwarfs, barely massive enough to sustain fusion, will outlive every other type of star by orders of magnitude. They'll still be burning when the universe is 100 times its current age. They'll watch galaxies collide and merge, watch the last giant stars die, and they'll keep burning steadily in the growing darkness. But eventually, every star exhausts its hydrogen. And what happens next is where things become truly spectacular. For a star like our Sun, the end begins quietly. As the hydrogen in the core runs out, fusion stops. Without radiation pressure to hold it up, the core contracts and heats up. But there's still hydrogen in a shell around the core, and that shell begins to fuse. The energy released causes the star's outer layers to expand dramatically. The star becomes a red giant. Our Sun will one day swell to enormous size, perhaps engulfing the orbits of Mercury and Venus, and possibly even Earth. Its surface will cool to a dull red, but its total energy output will increase. For a few 100 million years, it will burn helium in its core, fusing it into carbon and oxygen. But it won't have the mass to go further. When the helium runs out, there will be no more fusion. The core, now made of carbon and oxygen, will contract into a dense ember called a white dwarf. The outer layers will drift away as a beautiful planetary nebula, illuminated by the white dwarf's ultraviolet radiation. The white dwarf will remain, slowly cooling over trillions of years, eventually becoming a black dwarf, a cold, dark cinder, the final grave of a star like ours. But for massive stars, death is far more dramatic. When a star much larger than the Sun exhausts its core hydrogen, it doesn't stop at helium. It's massive enough to fuse helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon. Each stage happens faster than the last. Hydrogen fusion might last millions of years. Silicon fusion lasts less than a day. The star builds up a layered structure like an onion, hydrogen burning in the outermost shell, then helium, then carbon, and so on, all the way down to an iron core. And iron is where fusion ends. Fusing iron doesn't release energy, it consumes it. Iron is the most stable element. You can't profit, energetically speaking, from fusing it into heavier elements, so when the core becomes iron, the star's fate is sealed. With no fusion to provide outward pressure, the core collapses. In less than a second, the iron core, about 1.5 times the mass of the Sun, collapses into a sphere only about 20 kilometers across. The protons and electrons are crushed together, forming neutrons. A neutron star is born. The collapse is so sudden that the outer layers of the star are still falling inward when the core rebounds. The collision creates a shock wave that blasts outward, tearing the star apart in a supernova explosion. For a few weeks, that single exploding star can shine as brightly as an entire galaxy of 100 billion stars. The violence is unimaginable. In those final moments, temperatures reach billions of degrees. Elements heavier than iron, gold, platinum, uranium, are forged in the chaos and scattered into space. the shockwave races outward at a significant fraction of the speed of light, slamming into surrounding gas clouds and triggering the birth of new stars. Death gives rise to life, destruction seeds creation, and the neutron star left behind? It's one of the most extreme objects in the universe. A teaspoon of neutron star material would weigh about 1 billion tons. Its gravity is so intense that the escape velocity from its surface approaches half the speed of light. Some neutron stars spin hundreds of times per second, beaming radiation like cosmic lighthouses. These are called pulsars. But for the very most massive stars, even a neutron star isn't the end. If the core is more than about 3 times the mass of the Sun, not even neutron degeneracy pressure can hold it up. The collapse doesn't stop. The core continues to contract, becoming denser and denser, warping space-time more and more severely, until it crosses a threshold from which there is no return. It becomes a black hole, and that is a mystery profound enough to deserve its own chapter. Zoom out now. Pull back from individual stars, from their births and deaths, and see the larger pattern. Stars don't exist in isolation. They gather together by the billions into galaxies, vast islands of light separated by oceans of darkness. Our own galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars. It's a barred spiral galaxy, about 100,000 light-years across, with elegant spiral arms rotating slowly around a central bulge. At its heart lies a supermassive black hole 4 million times the mass of the Sun. We're located in one of the spiral arms, about 26,000 light-years from the galactic center. From our vantage point inside the disk, we see the Milky Way as a bright band stretching across the night sky. Billions of distant suns blurred together into a river of light. But the Milky Way is just one galaxy among trillions. In the observable universe, we estimate there are somewhere between 100 billion and 2 trillion galaxies. Each one contains billions or even trillions of stars. The numbers become so large they lose meaning. Try to picture 1 trillion galaxies, each with hundreds of billions of stars, and the mind simply stops. It can't hold that magnitude. We can only feel it, a kind of vertigo, an awe that borders on terror. Galaxies come in different shapes and sizes. There are spiral galaxies like ours with graceful arms trailing like cosmic whirlpools. There are elliptical galaxies, shaped like smooth footballs or spheres, often formed when 2 galaxies collide and merge. There are irregular galaxies, chaotic and misshapen, still evolving toward a more stable form. And then there are the smallest galaxies, dwarf galaxies, containing only a few billion stars. Dozens of these orbit the Milky Way like moons around a planet. But even more remarkable than the galaxies themselves is how they're arranged. For decades, astronomers have been mapping the distribution of galaxies across space. What they've found is stunning. Galaxies aren't scattered randomly through the universe. They're organized into an enormous structure called the cosmic web. Imagine soap bubbles pressed together. The galaxies cluster along the thin films where bubbles touch, forming vast filaments and sheets of light, stretching across hundreds of millions of light years. Between these filaments are immense voids, regions nearly empty of galaxies, where darkness reigns almost undisturbed. This is the large-scale structure of the universe, a web of light suspended in darkness shaped by gravity over billions of years. At the intersections of the filaments where multiple threads meet, galaxies pile up in enormous clusters. The Virgo cluster contains over 1,000 galaxies. The Coma cluster contains more than that. And these clusters themselves are grouped into superclusters, structures so vast that light takes hundreds of millions of years to cross them. Our local group, which includes the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and about 50 smaller galaxies, is part of the Virgo supercluster, which in turn is part of an even larger structure called the Laniakea supercluster, containing about 100,000 galaxies. These names, Virgo, Laniakea, sound poetic, almost mythological, but they describe real places, cosmic addresses. We live in a particular galaxy, in a particular cluster, in a particular supercluster, within a particular region of the observable universe. And here's the unsettling truth. We can only see a finite portion of the cosmos, about 93 billion light-years in diameter. That's the observable universe. Beyond that, light hasn't had time to reach us since the Big Bang. There could be more galaxies out there, more superclusters, more cosmic webs stretching away forever. We simply don't know. But even within the observable universe, our position is humbling. If the Milky Way were reduced to the size of a dinner plate, the distance to the nearest large galaxy, Andromeda, would be about 20 feet. The distance to the edge of the observable universe? About 2,000 miles. That's the scale we're dealing with. Andromeda, by the way, is heading toward us. In about 4.5 billion years, the Milky Way and Andromeda will collide. Not a violent crash. Galaxies are mostly empty space, but a slow, graceful merger over hundreds of millions of years. The two spiral galaxies will distort each other with gravity, forming tidal tails and triggering bursts of new star formation. Eventually, they'll settle into a single large elliptical galaxy. Astronomers have already named this future galaxy Milkomeda. Our Sun will likely survive the merger, though it might be flung into a different part of the new galaxy. By then, the Sun will be nearing the end of its life, beginning its expansion into a red giant. Earth, if it still exists, will be a scorched, lifeless world. But that's billions of years away. For now, the Milky Way and Andromeda orbit each other slowly, like dancers who haven't yet touched. Standing on Earth, looking up at the night sky, it's hard to grasp the scale of what you're seeing. That faint smudge in the constellation Andromeda. That's 2.5 million light-years away. You're seeing it as it was 2.5 million years ago, when our ancestors were just learning to make stone tools. The light has been traveling through the void all this time, uninterrupted, until it entered your eye just now. And Andromeda is one of our closest neighbors. Most galaxies are unimaginably farther away. The light from the most distant galaxies we've observed has been traveling for more than 13 billion years. We're seeing them as they were when the universe was young, when the first galaxies were just beginning to form. They look different from modern galaxies. Smaller, irregular, chaotic. We're watching the universe's adolescence. This is what telescopes allow us to do. Not just see far away in space, but far back in time. Astronomy is archaeology. We excavate the past by collecting ancient light. And what we've learned is this: the universe is vast beyond human comprehension. Structured in ways that suggest hidden patterns, governed by forces we're only beginning to understand. We are so small. Our entire history, every human who has ever lived, every civilization that has risen and fallen, all of it has happened on a single planet orbiting a single star in one of the spiral arms of an ordinary galaxy, which is itself just one of trillions. It's terrifying, and it's beautiful, because despite our insignificance, despite the overwhelming scale of reality, we're here, we exist, we think, we wonder. We send telescopes into space to gather ancient light and piece together the story of creation. We are tiny, but we are not nothing, and the universe is waiting for us to understand it. Here's a disturbing fact. We can only see about 5% of the universe. Everything we've talked about so far, stars, galaxies, planets, gas clouds, black holes, all the matter we can detect with our telescopes, all the atoms that make up everything we know. It accounts for only a tiny fraction of what actually exists. The rest is invisible, hidden, made of something we cannot see, cannot touch, and barely understand. Welcome to the era of dark matter and dark energy, the two greatest mysteries in modern cosmology. Let's start with dark matter, because at least we have some understanding of what it does, even if we don't know what it is. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a collection of over 1,000 galaxies. He measured how fast the galaxies were moving relative to each other and used that to estimate the cluster's total mass, using Newton's laws of gravity and the virial theorem. But something didn't add up. The galaxies were moving far, too quickly. According to his calculations, they should have been flung apart long ago. The visible matter in the cluster, all those stars and gas clouds, didn't produce enough gravity to hold the cluster together at those speeds. There had to be more mass. A lot more. Mass that wasn't emitting or reflecting light. Mass that was dark. Zwicky called it dunkel Materie, dark matter. But his ideas were largely ignored for decades. They were too strange, too unsettling. Surely most scientists thought there must be another explanation. Maybe we were miscounting the visible matter. Maybe our understanding of gravity was slightly off at these scales. Then, in the 1970s, astronomer Vera Rubin conducted studies that would fundamentally change our understanding of galaxies. She measured the rotation curves of spiral galaxies. How fast stars were moving at different distances from the galactic center. According to Newton's laws and our understanding of gravity, stars farther from the center should orbit more slowly, just like planets in our solar system. Mercury orbits the Sun much faster than Neptune does, because it's closer to the Sun's mass. But that's not what she found. Stars at the outer edges of galaxies were moving just as fast as stars closer to the center. The rotation curves were flat. The galaxies were rotating almost like solid disks, not like solar systems. This made no sense based on the visible matter alone. The only explanation was that galaxies contain far more mass than we can see. A vast halo of invisible matter extending well beyond the visible stars, providing additional gravity to hold the fast-moving outer stars in their orbits. This was shocking. It meant that the bright spiral of stars we see when we look at a galaxy, the thing we think of as the galaxy, is actually just a small component embedded in a much larger halo of invisible matter. Like a fly trapped in an invisible balloon, or a bright ornament hanging in a dark room. Today, we have overwhelming evidence for dark matter from multiple independent sources. We see its gravitational effects in galaxy clusters like Zwicky did. We see it in galaxy rotation curves like Rubin did. But we also see it in the way light bends around massive objects, a phenomenon called gravitational lensing. When light from a distant galaxy passes near a massive cluster of galaxies, the cluster's gravity bends space-time, and the light follows that curvature. The distant galaxy appears distorted, stretched into arcs or even multiple images. By analyzing these distortions, we can map where the mass is, even if we can't see it. And when we do this, we find that the mass distribution doesn't match the distribution of visible matter. There's a huge amount of additional mass, dark matter, creating the gravitational lensing effects. We've even mapped its distribution across the universe by observing how it warps the light from millions of distant galaxies. The resulting maps show that dark matter forms a kind of cosmic scaffolding, filaments and clumps that trace out the large-scale structure of the universe. Galaxies form where dark matter is densest, like cities built along highways. Dark matter doesn't interact with light. It doesn't absorb it, emit it, or reflect it. It's completely transparent to electromagnetic radiation. It interacts with ordinary matter only through gravity and possibly through the weak nuclear force, though that's uncertain. As far as we can tell, it passes right through us, through the Earth, through everything, like ghosts drifting through walls. Right now, as you listen to these words, countless dark matter particles are streaming through your body. You can't feel them. They don't interact with the atoms in your cells. They pass through as if you weren't there. And yet, their collective gravitational influence holds galaxies together and shapes the structure of the cosmos. And it's everywhere. For every kilogram of ordinary matter in the universe, there are about 5 kilograms of dark matter. It outweighs all the stars, all the planets, all the gas and dust by a factor of 6 to 1. The universe is dominated by something we've never directly detected. So what is it? We don't know. Physicists have proposed various candidates: exotic particles like WIMPs, weakly interacting massive particles, or axions. But despite decades of searching, we haven't directly detected dark matter. Experiments deep underground, shielded from cosmic rays, sit waiting for the telltale signal of a dark matter particle colliding with an atomic nucleus. So far, nothing. Some researchers are beginning to wonder if we're thinking about this wrong. Maybe dark matter isn't a particle at all. Maybe our understanding of gravity needs to be modified at large scales. This idea is called modified Newtonian dynamics, or MOND. But most physicists remain skeptical. Dark matter seems to be the simplest explanation, even if we don't yet know what it is. And dark matter, strange as it is, pales in comparison to the second mystery: dark energy. In the late 1990s, 2 teams of astronomers were studying distant supernovae, using them as standard candles to measure cosmic distances and determine how the expansion of the universe was slowing down over time. Because that's what everyone expected: that gravity should be gradually slowing the expansion, perhaps even causing the universe to eventually collapse back on itself in a big crunch. But that's not what they found. The expansion wasn't slowing down, it was speeding up. The universe is accelerating. This discovery was so unexpected, so shocking, that the teams checked and rechecked their data for years before publishing. But the result held. In 2011, the leaders of the 2 teams were awarded the Nobel Prize in Physics. Something is pushing the universe apart. Something that acts as a kind of anti-gravity, permeating all of space and causing space itself to expand at an ever-increasing rate. We call it dark energy, but that's just a placeholder name. We have no idea what it actually is. Dark energy makes up about 68% of the universe's total energy density. Dark matter accounts for about 27%. Ordinary matter, everything we can see, everything we're made of, is only about 5%. We are a minority, a tiny fraction. Living in a universe dominated by invisible forces we don't understand. Think about that for a moment. The universe we can see and touch and measure directly is a thin film on the surface of a vast ocean. Most of reality is hidden from us. Not just far away or obscured, but fundamentally undetectable with our current technology, and perhaps even with our current physics. It's like being in a dark room and realizing that the walls are much farther away than you thought, that the room is actually enormous, extending in directions you can't perceive. That what you thought was the whole world is actually just a tiny corner of something vastly larger. Some physicists find this exciting. It means there's still so much to discover, so many mysteries left to solve. Others find it humbling. even unsettling. We thought we understood the universe, at least in broad strokes. We thought we knew what it was made of. We were wrong. The visible universe, all the stars and galaxies, all the light and matter we've spent centuries studying, is just the foam on the waves. The deep ocean beneath is dark, mysterious, and mostly unknown. And that ocean is growing. Dark energy is causing space to expand faster and faster. Distant galaxies are accelerating away from us. Eventually, billions of years from now, they'll be receding faster than the speed of light, not because they're moving through space that quickly, but because space itself is expanding between us and them. The light they emit will never reach us. They'll cross what's called the cosmic event horizon and disappear forever from our view. Future astronomers, if they exist, will look up at a sky with far fewer galaxies than we see today. The universe will appear smaller, emptier, and if they don't have records from our time, they might never realize how much they've lost. Dark matter and dark energy aren't just academic curiosities. They're the dominant forces shaping the universe's fate. They determine whether the universe will expand forever or eventually collapse. They shape the formation of galaxies and the distribution of matter across cosmic scales. And we don't understand them at all. This is the invisible universe, a cosmos made mostly of mystery, where the familiar is the exception and the unknown is the rule. It's humbling. It's terrifying, and it's a reminder that no matter how much we learn, no matter how sophisticated our telescopes and experiments become, the universe will always be deeper, stranger, and more mysterious than we imagined. We are explorers sailing on a vast ocean, and we've only just begun to realize how much water lies beneath us. Some things exist at the boundary of what's possible, at the edge where physics meets philosophy, where mathematics describes something so extreme it seems like science fiction. Black holes are that boundary. A black hole is, fundamentally, a region of space-time where gravity has become so intense that nothing can escape. Not matter, not light, not even information. It's a place where the normal rules break down, where time and space trade places, where the very structure of reality tears itself apart. They're real. We've detected them. We've even photographed one. In April 2019, the Event Horizon Telescope, a network of radio telescopes spanning the globe, working together as a single Earth-sized instrument, released the first image of a black hole's event horizon. It showed a dark circle surrounded by a bright ring of glowing gas, the supermassive black hole at the center of the galaxy, M87, about 55 million light-years away. The image was blurry, orange-tinted, ghostly, but it was real. Direct visual evidence of one of the universe's most bizarre objects. To understand black holes, we need to understand space-time. Einstein's general relativity tells us that space and time aren't separate, static things. They're woven together into a four-dimensional fabric called space-time, and massive objects warp that fabric. Imagine placing a bowling ball on a stretched rubber sheet. The ball creates a depression, and if you roll a marble nearby, it will curve towards the ball. That's a simplified picture of how gravity works. Objects move along the curves in space-time created by mass. A black hole is what happens when you compress so much mass into such a small volume that space-time curves infinitely. The rubber sheet doesn't just dip, it tears. A hole opens up, and anything that crosses the edge of that hole, the event horizon, can never come back. The event horizon isn't a physical surface. There's no wall, no barrier. If you were falling toward a black hole and crossed the event horizon, you wouldn't notice anything special at that exact moment. You'd just pass a mathematical boundary, a point of no return. But from that moment on, every direction you could move would lead closer to the center. Even if you pointed your spaceship directly away and fired your engines at full thrust, you'd still fall inward. Not because your engines are too weak, but because space-time itself is so warped that outward doesn't exist anymore. And if you were watching someone else fall in, you'd see something strange. As they approached the event horizon, they'd appear to slow down, moving slower and slower, their image redshifting, fading to black. You'd never actually see them cross the horizon. From your perspective, they'd be frozen forever at the edge, taking an infinite amount of time to fall in. This is gravitational time dilation. Time runs slower in strong gravitational fields. Near the event horizon, time slows to a crawl. At the horizon itself, time stops. Or rather, from an outside observer's perspective, it does. But from the perspective of the person falling in, time passes normally. They fall through the event horizon in finite time, and then things get worse. As you fall deeper into the black hole, tidal forces become extreme. The difference in gravitational pull between your head and your feet becomes enormous. You're stretched vertically and compressed horizontally, a process astronomers have cheerfully named spaghettification. Your body would be pulled apart, atom by atom, long before you reach the singularity at the center. The singularity. That's where all the mass of the black hole is concentrated, a point of infinite density, zero volume, where the laws of physics as we know them simply stop working. General relativity predicts that singularities exist at the hearts of black holes, but it also admits that its own equations break down there. We need a theory of quantum gravity to understand what really happens at the singularity, and we don't have one yet. Maybe singularities don't actually exist. Maybe quantum effects prevent infinite compression, creating some kind of exotic quantum state instead. Or maybe our entire understanding of space and time needs to be revised. We don't know. There are different types of black holes, formed in different ways. Stellar mass black holes form when massive stars die, as we discussed earlier. They range from about 3 times the mass of the Sun to perhaps 100 solar masses. Thousands of these are scattered throughout our galaxy. Then there are supermassive black holes, millions or billions of times the mass of the Sun, lurking at the centers of most large galaxies. Our Milky Way's central black hole, Sagittarius A star, is about 4 million solar masses. The one at the center of M87, the one we photographed, is about 6.5 billion solar masses. How supermassive black holes formed is still somewhat mysterious. They're too massive to have formed from a single star. Perhaps they grew by consuming gas and stars over billions of years. Perhaps they formed directly from the collapse of massive gas clouds in the early universe. Perhaps smaller black holes merged together repeatedly. Likely, all these processes contributed, and recently, astronomers have discovered evidence for intermediate mass black holes, ranging from hundreds to thousands of solar masses, filling the gap between stellar mass and supermassive black holes. These might be the seeds that eventually grew into the supermassive monsters. Black holes aren't just cosmic curiosities. They play an active role in shaping galaxies. As matter falls into a supermassive black hole, it forms an accretion disk, a swirling disk of gas heated to millions of degrees, shining brightly across the electromagnetic spectrum. The most luminous objects in the universe are quasars, supermassive black holes actively feeding, visible across billions of light years. The energy released by infalling matter can blow powerful winds out into the surrounding galaxy, regulating star formation and affecting the galaxy's evolution. Black holes and galaxies co-evolve, each shaping the other over cosmic time. But perhaps the strangest thing about black holes is what they do to information. According to quantum mechanics, information cannot be destroyed. The state of a system at one time completely determines its state at any future time, at least in principle. But if something falls into a black hole and crosses the event horizon, where does the information about its quantum state go? Is it destroyed? That would violate quantum mechanics. Is it preserved somehow? This is the black hole information paradox, and it's been debated by physicists for decades. Stephen Hawking spent much of his career working on this problem. In the 1970s, he proved that black holes aren't completely black. They emit a faint thermal radiation, now called Hawking radiation, due to quantum effects near the event horizon. Given enough time, a black hole will completely evaporate, leaving nothing behind. But if the black hole evaporates, what happens to the information about everything that fell in? Hawking initially argued it was destroyed, but later changed his mind. Current research suggests the information might be preserved in subtle correlations in the Hawking radiation, or encoded on the event horizon itself, but we still don't have a complete answer. Black holes sit at the intersection of general relativity and quantum mechanics, the two great pillars of modern physics. And those two theories are fundamentally incompatible. General relativity describes gravity and space-time on large scales. Quantum mechanics describes the behavior of particles and fields on tiny scales. Both theories work brilliantly in their respective domains, but they contradict each other when you try to apply them to black holes or the Big Bang singularity. We need a theory of quantum gravity, a unified framework that merges general relativity and quantum mechanics into a single, coherent picture. String theory, loop quantum gravity, and other approaches are attempting to build such a theory, but we're not there yet. The math is fiendishly difficult, and we have almost no experimental data to guide us. Black holes are trying to teach us something. They're places where nature has set up an experiment we can't yet perform in our laboratories, pushing physics to its absolute limits. They're showing us where our theories break down, pointing the way toward a deeper understanding. And they're a reminder that the universe contains things stranger than we ever imagined. Objects so extreme that merely existing challenges our understanding of reality. Places where time stops, where space tears, where the familiar distinctions between past, present, and future might blur or disappear entirely. If you could somehow survive falling into a black hole, beyond the spaghettification, beyond the singularity, some solutions to Einstein's equations suggest you might emerge in another region of space-time, another universe, perhaps, a white hole, the time reverse of a black hole. These are purely theoretical. We have no evidence they exist. But the mathematics allows for them. Black holes might be tunnels, bridges, doorways to elsewhere. Or they might simply be the universe's ultimate one-way door. Places where things go in and never come out. Cosmic dead ends. Either way, they're magnificent. Terrible and beautiful in equal measure. A reminder that the universe is under no obligation to make sense to us, to be comprehensible or comfortable. Black holes exist whether we understand them or not, and they're waiting, patient and inevitable, at the edge of reality. What is time? It seems like a simple question. Time is what clocks measure. Time is what separates the past from the future. Time flows forward, one second after another, unchanging and absolute. Except, it isn't. Time is far stranger than it appears. It's flexible, relative, intertwined with space in ways that violate every intuition we've built up through everyday experience. And understanding time, really understanding it, requires us to let go of almost everything we think we know. Let's start with Einstein. In 1905, Albert Einstein published his special theory of relativity, which revealed something shocking. Time is not absolute. It doesn't tick at the same rate for everyone. How fast time passes depends on how fast you're moving. Imagine two twins. One stays on Earth, the other boards a spaceship and travels to a distant star at 99%, the speed of light, then returns. When the traveling twin arrives home, they've aged only a few years. But their sibling on Earth has aged decades. This isn't a trick or an illusion. Time genuinely passed more slowly for the traveling twin. Their clocks ran slower, their metabolism ran slower, their thoughts unfolded more slowly, all from the Earth twins' perspective. This is time dilation, and it's been confirmed by countless experiments. Atomic clocks on airplanes tick at different rates than identical clocks on the ground. GPS satellites have to account for relativistic time dilation, or they'd accumulate errors and become useless within hours. Time isn't a universal river carrying everyone along at the same rate. It's personal. Your time, my time. Each of us moves through time at our own pace, depending on our motion and the gravitational field we're in. Which brings us to Einstein's second great insight. Gravity affects time too. In 1915, Einstein published his general theory of relativity, which revealed that gravity isn't a force in the traditional sense. It's the curvature of space-time. Mass and energy warp space-time, and objects move along the curves. What we experience as gravity is really just following the natural paths, the geodesics, through curved space-time. And when space-time is curved by gravity, time is affected. Time runs slower in stronger gravitational fields. A clock at sea level ticks slightly slower than a clock on a mountaintop. A clock on the surface of the sun runs slower than a clock on Earth. And near a black hole, time slows to a crawl. This isn't just theory, it's measurable. In 1971, physicists flew atomic clocks around the world on commercial airliners and compared them to clocks that stayed on the ground. The traveling clocks had aged slightly less, nanoseconds, but measurable. Exactly as relativity predicted, time is real. But it's not what we thought it was. And here's where things get even stranger. If time is relative, if it passes at different rates for different observers, then what about now? What does it mean for two events to happen at the same time? The answer, according to relativity, is that simultaneity is relative too. Two events that appear simultaneous to one observer might not be simultaneous to another observer moving at a different velocity. There's no universal present moment shared by everyone in the universe. Your now is different from mine if we're in relative motion. This has profound implications. It means the universe doesn't unfold moment by moment, like frames in a movie. Instead, all of space-time exists together, past, present, and future, as a single four-dimensional structure called the block universe. From this perspective, everything that has happened and everything that will happen is already out there in space-time, just as much as distant places in space are already out there. Your birth, your childhood, this moment right now, and your death are all equally real, just at different coordinates in space-time. This view is called eternalism, and it's what relativity seems to suggest. But it raises uncomfortable questions. If the future already exists, do we really have free will? Is the flow of time an illusion? Why do we remember the past, but not the future? These are deep philosophical questions without clear answers. Physics can tell us how time behaves, but it struggles to explain why time feels the way it does. Why we experience a present moment, moving forward, separating a fixed past from an open future. Some physicists think the flow of time is indeed an illusion, a quirk of consciousness or thermodynamics. Others argue that time is fundamental, that something is missing from our current theories. The debate continues. But let's go deeper. What if time isn't fundamental at all? What if it's emergent, a phenomenon that arises from something more basic, like temperature emerges from the motion of atoms? This is the view gaining traction in quantum gravity research. In theories like loop quantum gravity and some formulations of string theory, time disappears at the deepest level. The fundamental equations don't include time. Space-time itself is built from more primitive, timeless ingredients. From this perspective, time is something that emerges only at larger scales, in the classical limit where quantum effects average out. At the Planck scale, the smallest possible length and time scales, the concepts of before and after might not even apply. Reality at that level might be timeless, a static structure from which the illusion of time emerges. This is speculative, but it's taken seriously by leading physicists. Because as we probe deeper into the nature of reality, time keeps showing its cracks, its inconsistencies, its refusal to fit neatly into our theories. Meanwhile, space is equally strange. We think of space as empty, as nothing. But quantum field theory tells us that even empty space is seething with activity. Virtual particles pop in and out of existence. Quantum fields fluctuate. The vacuum isn't empty, it's a roiling quantum foam. And space itself might not be continuous. Just as matter is made of atoms, space might be made of discrete units at the Planck scale. Tiny pixels or loops or strings stitched together to create the smooth space-time we experience. If that's true, then zooming in far enough, space wouldn't look smooth at all. It would look grainy, pixelated, fundamentally discontinuous. Distance and duration would be quantized, coming in minimum-sized chunks that can't be subdivided further. But we can't test this directly. The Planck scale is about 10 to the power of minus 35 meters, 20 orders of magnitude smaller than a proton. We'll never build a microscope powerful enough to see it. We can only probe it indirectly through mathematics and cosmological observations. So here we are. Time is relative, space is curved. The present moment is observer-dependent. The flow of time might be an illusion. And at the deepest level, space-time itself might be emergent, built from something we don't yet understand. The stage on which the cosmic drama unfolds, the very fabric of reality, is far stranger than Newton or even Einstein imagined. And yet, we navigate it successfully every day. We make plans for the future. We remember the past. We move through space and time as if they were solid, reliable, unchanging. In a sense, that's a testament to how deeply rooted our intuitions are. We evolved in a world where relativistic effects are negligible, where space seems flat and time flows steadily. Our brains are wired for that world. So when physics reveals that reality is actually curved, relative, and possibly emergent, it feels wrong, counterintuitive. But intuition isn't always a reliable guide. The universe doesn't care about what feels natural to us. It operates according to its own rules, and our job is to discover those rules, even when they defy common sense, time, and space. The coordinates of existence, the framework within which everything happens, and we still don't truly understand them. Perhaps that's fitting. These are the most basic aspects of reality, the stage on which everything else plays out. If we fully understood them, we'd probably have to revise our understanding again, because there would be something deeper beneath them. Maybe there's no bottom. Maybe every answer just reveals a deeper question. Or maybe we're close to something fundamental. Maybe in our lifetimes, physicists will crack the code, find the theory of quantum gravity, and understand what space-time really is. Until then, we live with mystery. We move through time, not quite sure what time is. We exist in space, not quite sure what space is. But we move, we exist, we think. And somehow, despite the strangeness, despite the relativity and the curvature and the quantum foam, we find meaning in this universe. That, perhaps, is the greatest mystery of all. In all the universe, across all those trillions of galaxies, among all those countless stars and planets, are we the only ones? It's one of humanity's oldest questions, and despite decades of searching, we still don't know the answer. Consider the numbers. In our galaxy alone, there are hundreds of billions of stars. Many, perhaps most of those stars, have planets. Recent data from the Kepler Space Telescope and other planet-hunting missions suggest that rocky planets in the habitable zone, the region where liquid water could exist on the surface, are common. There might be billions of potentially habitable planets just in the Milky Way. And remember, the Milky Way is just one galaxy among trillions. If even a tiny fraction of those planets developed life, the universe should be teeming with it. And if even a tiny fraction of those life-bearing worlds developed intelligent, technological civilizations, there should be thousands or millions of them in our galaxy alone. So where is everyone? This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where are they?" If advanced civilizations are common, we should see evidence of them. Radio signals, megastructures, evidence of astroengineering projects. Something. But the universe is silent. We've been listening since 1960, when astronomer Frank Drake pointed a radio telescope at nearby stars in the first systematic search for extraterrestrial intelligence. Since then, SETI, the search for extraterrestrial intelligence, has scanned millions of radio frequencies looking for patterns that might indicate an artificial signal. Nothing. No unambiguous detections, no hello from the stars. There are many possible explanations for this silence. Maybe life is rare. Maybe the jump from simple life to complex, multicellular life is an incredibly unlikely fluke. Earth's history suggests that single-celled life appeared quickly, but complex life took billions of years to evolve. Maybe the universe is full of bacteria, but intelligence is vanishingly rare. Or maybe intelligence is common, but technological civilizations don't last long. They might destroy themselves through war, environmental collapse, or uncontrolled technology before they become visible across interstellar distances. If the average lifespan of a technological civilization is only a few hundred years, the odds of two civilizations existing at the same time, close enough to detect each other, become very small. This is a sobering thought. It suggests that our own civilization might be in danger, that the Great Filter, some catastrophic event or challenge that prevents civilizations from lasting, might still be ahead of us. Or maybe we're looking in the wrong way. Maybe advanced civilizations don't use radio. Maybe they use technologies we haven't imagined yet, communicating through channels we can't detect. Maybe they're out there, but we're like ants trying to understand the internet, too primitive to even recognize the signals. Or perhaps they're deliberately hiding. Maybe there's a galactic club of advanced civilizations, and they're observing us quietly, waiting until we reach a certain level of development before revealing themselves. This is the zoo hypothesis. The idea that Earth is like a nature preserve, and contact is prohibited until we're ready. Or maybe, and this is the loneliest possibility, maybe we're the first. Maybe in this region of the galaxy, at this particular moment in cosmic history, we're the first species to achieve intelligence and technology. We're the pioneers, the firstborn. If that's true, it places an enormous responsibility on us. Not to destroy ourselves, to survive long enough to become the ancient, advanced civilization that future species will search for. We don't know which explanation is correct. All we have is silence. But absence of evidence is not evidence of absence. Just because we haven't detected aliens doesn't mean they don't exist. The universe is vast and we've barely scratched the surface of the search. Meanwhile, we're learning more about potentially habitable worlds. In our own solar system, we've discovered places that might harbor life. Not Earth-like life on the surface of a planet, but perhaps microbial life in subsurface oceans. Jupiter's moon Europa has a global ocean of liquid water beneath its icy crust, kept warm by tidal heating. Saturn's moon Enceladus also has a subsurface ocean, and geysers of water vapor shoot out from its south pole. We've flown through those geysers and detected organic molecules. Even Mars, cold and dry today, was once warm and wet. We've found ancient riverbeds, dried lake beds, evidence of a thick atmosphere billions of years ago. If life arose on Mars back then, could it still exist underground in aquifers or ice deposits? NASA's Perseverance rover is currently collecting samples from Mars that will eventually be returned to Earth for analysis. In the next decade, we'll send missions to Europa and Enceladus, possibly even drilling through the ice to sample the oceans below. We might not have to look to other star systems to find extraterrestrial life. It might be right here in our own cosmic neighborhood. And beyond our solar system, we're discovering exoplanets at an astounding rate. As of now, we've confirmed over 5,000 exoplanets, with thousands more candidates waiting for verification. Some are gas giants larger than Jupiter. Some are small, rocky worlds similar to Earth. A few are in the habitable zone of their stars. The James Webb Space Telescope is now analyzing the atmospheres of some of these exoplanets, looking for biosignatures, gases like oxygen and methane that, in combination, might indicate biological activity. We haven't found definitive evidence yet, but we're looking. And the technology improves every year. In a few decades, we might point our telescopes at a distant world and see unmistakable signs of life. Oxygen, chlorophyll, lights on the night side indicating cities, radio signals. Or we might not. The universe might remain silent. Either answer is profound. If we find life, especially intelligent life, it will be the most important discovery in human history. It will transform our understanding of biology, evolution, and our place in the cosmos. We'll know we're not alone. That consciousness has emerged elsewhere, that the universe is capable of generating beings who think and wonder and build. But if we don't find life, if we search for centuries and find only silence, that's profound too. It means we're rare, precious, perhaps unique. It means the universe is mostly empty, and consciousness is a fragile flame that's only ignited in the rarest circumstances. Both possibilities are awe-inspiring. Both are humbling. For now, we wait, we listen, we search, and we contemplate what it means to be alone in the dark, sending out signals into the void, hoping for an answer. The universe is vast. Life might be everywhere, or it might be incredibly rare. Intelligence might be common, or we might be the only ones asking these questions. We don't know. We can't know. Not yet. But the search continues. Because even if we never find anyone else, the act of searching changes us. It makes us think about who we are, what we value, what kind of future we want to build. And if we do find someone, some other consciousness looking back at us from across the stars, that moment will mark the beginning of a new chapter in cosmic history. Until then, we're here. Alone or not, we're here. Thinking, wondering, reaching out into the dark. And maybe, somewhere out there, someone is reaching back. What if our universe isn't the only one? It sounds like science fiction, but some of the most respected physicists in the world take the idea seriously. The multiverse, the concept that our universe is just one among many, perhaps infinitely many, arises naturally from several different areas of theoretical physics. Let's explore the possibilities. First, there's the inflationary multiverse. Remember cosmic inflation, the period of exponential expansion in the universe's first fraction of a second? The theory that drives inflation involves a quantum field called the inflaton field. In most regions of space, this field eventually settles into a low-energy state, and inflation stops. That's what happened in our observable universe. But quantum mechanics tells us that fields fluctuate. In some regions, those fluctuations might cause inflation to continue. Those regions expand exponentially, creating vast new volumes of space. And within those regions, further fluctuations create even more inflating regions. This process never ends. It's called eternal inflation. Our universe is just one bubble where inflation happened to stop. But beyond our cosmic horizon, inflation continues, spawning an endless succession of bubble universes, each with its own Big Bang, its own physics, potentially its own laws of nature. These bubble universes are causally disconnected from us. Light from them can never reach us because the space between us is expanding faster than light can travel. They're forever beyond our ability to observe, but they might exist. Entire universes as vast as ours or vaster, with their own galaxies, stars, planets, maybe even life, and we can never know anything about them. Then there's the many worlds interpretation of quantum mechanics. Quantum mechanics is famously strange. Before you observe a quantum system, it exists in a superposition, a combination of multiple possible states. But when you measure it, the superposition collapses, and you see one definite outcome. Schrödinger's cat in the box is both alive and dead until you open the box and look. Then it's one or the other. But why does observation cause collapse? What's special about measurement? This has bothered physicists since the 1920s. In 1957, physicist Hugh Everett proposed a radical solution. Nothing collapses. The superposition is real. When you open the box, the universe splits into two branches. In one branch, the cat is alive. In the other, it's dead. Both branches are equally real. You just can't perceive the other branch anymore because you're now in one of them. This is the many worlds interpretation. Every quantum event causes the universe to branch into multiple copies, one for each possible outcome. The branching happens constantly, everywhere, all the time. There are unimaginably many parallel versions of reality, differing in every possible quantum outcome. In some of those branches, you made different decisions. In some, historical events unfolded differently. In some, the dinosaurs never went extinct. In some, life never arose on Earth at all. All of it exists according to many worlds, not as separate bubble universes in space, but as parallel branches of the wave function, the quantum description of reality. This interpretation is controversial. Many physicists find it extravagant, violating Occam's razor, the principle that we shouldn't multiply entities beyond necessity. Others argue it's actually the simplest interpretation because it doesn't require any mysterious collapse mechanism. The math just plays out naturally. We can't test it. We can't observe the other branches, but it's a logically consistent way of understanding quantum mechanics. Then there's the string theory landscape. String theory attempts to unify general relativity and quantum mechanics by proposing that the fundamental constituents of reality aren't particles, but tiny vibrating strings. Different vibration modes correspond to different particles. But string theory requires extra spatial dimensions, 10 or 11 depending on the version. The extra dimensions are curled up so small we can't perceive them directly. And there are many ways those dimensions can be curled up, roughly 10 to the power of 500 different ways. Each configuration gives rise to a different set of physical laws, different particle masses, different forces, different constants of nature. Each configuration is a different vacuum state, a different possible universe. This enormous collection of possibilities is called the string theory landscape. If string theory is correct, and if some version of eternal inflation is also correct, then all those possible universes might actually exist somewhere in the multiverse, each in its own bubble. Our universe would be just one valley in an enormously complex landscape of possibilities. And finally, there's the mathematical multiverse proposed by cosmologist Max Tegmark. Tegmark asks, why does mathematics describe the universe so well? Maybe it's not that the universe is described by math. Maybe the universe is math. Maybe physical reality is just a mathematical structure, and we're patterns within that structure. If that's true, then every mathematically consistent structure exists as a real universe somewhere. Not in physical space, but in a more abstract sense. Platonic reality. The space of all possible mathematical structures. This is the ultimate multiverse. Not just other universes with different laws of physics, but universes with entirely different mathematical structures. Some might have time, some might not. Some might be describable, others might be too alien for consciousness like ours to even exist. These are speculative ideas. We have no direct evidence for any version of the multiverse. We might never have such evidence because by definition, other universes are beyond our ability to observe. But these ideas emerge naturally from our best theories. They're not arbitrary inventions. They're logical consequences of inflation, quantum mechanics, string theory, and mathematics itself. Still, some physicists are skeptical. They argue that if a theory predicts things we can never observe, it's not really science anymore, it's metaphysics. Interesting perhaps, but not testable. Others counter that we've always extrapolated beyond what we can directly observe. We believe in atoms even though we can't see individual atoms with our eyes. We believe in the interiors of stars even though we can't visit them. We believe in the far side of the moon even when we can't see it. Science often involves inferring the existence of unobservable things from the things we can observe. If a theory makes testable predictions in our universe, and those predictions turn out correct, we have reason to take seriously the theory's other implications, even if those implications are unobservable. So maybe the multiverse is real. Maybe our universe, vast as it is just one tiny bubble in an infinite foam. Maybe every quantum event creates new branches. Maybe every possible mathematical structure exists. Or maybe not. Maybe we're it. One universe, the only one. Either way, it's staggering to contemplate. If the multiverse exists, then everything that can happen does happen, somewhere. Every possibility is realized. You exist in countless variations. History has played out in every conceivable way. The universe is infinitely richer, infinitely stranger than we can imagine. But if this is the only universe, then we're witness to something unique. This particular arrangement of particles, this particular history, exists only here and only once. We're not one sample from an infinite collection. We're singular, and that makes existence feel both more fragile and more precious. We don't know which is true. We might never know, but we can ask the question. We can follow the mathematics and see where it leads. We can imagine what lies beyond the boundaries of the observable, even if we can never cross those boundaries. We are explorers of ideas as much as explorers of space. And some of the most important discoveries happen not with telescopes, but with equations and thought experiments. The multiverse, if it exists, would be the ultimate example of what lies beyond our reach. Not beyond the horizon of our observable universe, but beyond the boundary of what's observable in principle. Other universes, other realities, other versions of you reading other versions of this sentence. It's dizzying, unsettling, magnificent. And it reminds us once again that reality is deeper than we ever imagined, that every time we think we've grasped the full picture, we discover there's more. Always more, infinity stacked on infinity, mysteries within mysteries, and we've barely begun to explore. Let's return for a moment to Earth, to ourselves. We've journeyed far. We've explored the birth of the universe, the lives of stars, the structure of galaxies, the mysteries of dark matter and black holes. We've contemplated time, space, the possibility of other life, and even other universes. But what about us? Where do we fit into this immense, ancient, impersonal cosmos? We are small. That's undeniable. Our planet is a pale blue dot, barely visible from the edge of our own solar system, invisible from the nearest star. Our entire history, every empire, every war, every work of art, every love story, has unfolded on the surface of this tiny world. From a cosmic perspective, we're insignificant, fleeting. The universe existed for 13.8 billion years before we appeared, and it will continue for trillions of years after we're gone. Our moment in time is brief. Our reach in space is limited. We haven't even left our own solar system yet. And yet, we're also remarkable. We are matter that became alive, that became conscious, that became curious. We're the universe looking at itself. We're atoms arranged in such a way that we can contemplate atoms. We're star stuff that wonders about stars. Consciousness is, as far as we know, rare. Maybe very rare. It took Earth billions of years to produce it. And once it emerged, it took millions more years to evolve into something capable of abstract thought, of language, of science. We are recent, we are fragile, but we are also extraordinary. Think about what we've accomplished. In just a few thousand years, a blink of cosmic time. We've gone from hunter-gatherers to spacefarers. We've decoded the structure of matter, mapped the human genome, discovered the age of the universe, detected gravitational waves, photographed black holes. We've built telescopes that can see back to the dawn of time. We've sent probes to the edge of the solar system and beyond. Voyager 1, launched in 1977, is now in interstellar space, carrying a golden record with sounds and images from Earth. A message to any civilization that might find it billions of years from now. We've looked at distant galaxies and understood their light. We've peered into atoms and understood their structure. We've contemplated the beginning of time and the end of the universe. This is astonishing. We take it for granted because we live immersed in it. But step back for a moment and see it clearly. We are tiny creatures on a tiny world, and we've managed to understand a universe billions of light years across. We've decoded its history. We've predicted its future. We've grasped the laws that govern everything from subatomic particles to superclusters of galaxies. How is this possible? The universe didn't have to be comprehensible. The laws of physics didn't have to be discoverable by human minds. The mathematics we use to describe reality didn't have to align so perfectly with reality itself. But they do. And that suggests something profound. We're not separate from the universe. We're part of it. We're woven into its fabric. The patterns we see in nature are patterns that also exist within us because we're made of the same stuff, governed by the same laws. When we do science, we're not imposing order on chaos. We're discovering the order that was already there. We're revealing the universe's deep structure that existed long before minds evolved to perceive it. And in doing so, we give the universe meaning. Not objective, cosmic meaning. The universe doesn't care whether we exist or not, but subjective, human meaning. The meaning that comes from understanding, from appreciating beauty, from feeling awe. A sunset is just photons scattering off atmospheric particles. But when you watch a sunset and feel moved by its beauty, that emotion is real. That experience adds something to the universe. Not much, perhaps, in the grand scheme, but something. We are the universe's way of experiencing beauty, of knowing itself, of caring about itself. And that's not insignificant. But with this capacity comes responsibility. We are, as far as we know, the only species on Earth capable of causing our own extinction. Through nuclear weapons, environmental destruction, engineered pandemics, or uncontrolled artificial intelligence, we could end our story prematurely. If we do, the universe will continue without us. Stars will burn, galaxies will collide, black holes will evaporate. Nothing will change on cosmic scales, but something precious will be lost. A voice, a perspective, a way of knowing. If consciousness is rare, and it might be very rare, then every conscious species has a kind of cosmic value. Not because some deity values us, but because consciousness itself is a remarkable phenomenon. When it emerges, when matter organizes itself into patterns capable of thought and wonder, that's something worth preserving. We don't know if there are other conscious species in the universe. If there are, we haven't met them. We might be alone, or we might be one among many. But either way, our existence matters. We have a choice. We can destroy ourselves, extinguishing this brief spark of consciousness. Or we can survive, grow, spread beyond our fragile world, and become one of the long-lived civilizations that shapes the future of the galaxy. Neither choice is guaranteed. The universe won't save us. We have to save ourselves. This is the challenge of our time, not just to explore the cosmos, but to ensure we survive long enough to do so. To build a civilization that can last not just centuries, but millennia or longer. To become worthy of the cosmic inheritance we've been given. And make no mistake, it is an inheritance. The atoms in our bodies were forged in stars. The energy that powers our civilization comes from nuclear reactions that mirror those in stellar cores. The planet we live on formed from the debris of ancient supernovae. We are made from the ashes of dead stars, and we carry their legacy forward. We are the universe's children, even if the universe doesn't know we exist. So what's our purpose? If the universe doesn't offer meaning, where do we find it? We create it. We define it. We choose what matters. For some, it's exploration, the drive to see what's beyond the next horizon, to visit other worlds, to search for life among the stars. For some, it's understanding, the quest to solve the remaining mysteries, to find the theory of everything, to know how reality works at its deepest level. For some, it's preservation, protecting the biosphere, ensuring that life on Earth flourishes, safeguarding the planet for future generations. For some, it's creation, art, music, literature, culture, the distinctly human expressions that give texture and richness to existence. There's no single answer, but all these paths share something. They're forward-looking. They assume we have a future, They assume there's more to discover, more to create, more to become. And that assumption is worth holding on to, because the alternative, despair, nihilism, the belief that nothing matters, is self-fulfilling. If we believe we have no future, we won't build one. But if we believe that despite our smallness, despite the vast indifference of the cosmos, we matter, then we can act as if we matter. We can build telescopes, we can write equations, we can make art, we can explore, we can reach out into the infinite and touch it, if only for a moment. We are small, but we are not nothing. We are the universe's way of knowing itself. And that is enough. We've looked backward through time, to the Big Bang, to the first stars. Now let's turn our gaze forward, not just years or centuries, but billions of years, trillions of years, into the deep future where the universe we know will have changed beyond recognition. Time is patient. The universe has all the time in the world, literally. And what happens over cosmic timescales is both beautiful and terrifying. Let's start close to home. In about 1 billion years, the sun will have grown about 10% brighter than it is today. That might not sound like much, but it will be enough to trigger a runaway greenhouse effect on Earth. The oceans will evaporate, the atmosphere will thicken, with water vapor trapping more heat. Surface temperatures will soar to hundreds of degrees. Earth will become uninhabitable, a scorched world like Venus. If humanity still exists, we'll have had to move, perhaps to Mars, which by then might be warming as the sun's increased luminosity makes it more habitable. Perhaps to the moons of Jupiter or Saturn. Or perhaps we'll have left the solar system entirely, spreading to other stars. In 5 billion years, the sun will begin its transformation into a red giant. It will exhaust the hydrogen in its core and start fusing hydrogen in a shell around the core. The star will swell, growing hundreds of times larger. Its outer layers will engulf Mercury, then Venus, and possibly Earth itself. Even if Earth survives, it will be a dead cinder, orbiting close to the bloated red sun, its surface melted and reformed countless times. But let's think bigger. Let's zoom out from our solar system and watch what happens to the galaxy. In about 4 billion years, the Andromeda Galaxy will collide with the Milky Way. From Earth, if anyone is still watching from Earth, Andromeda will grow larger in the night sky over millions of years. Eventually, it will dominate the sky, a swirl of stars stretching from horizon to horizon. The collision itself will take hundreds of millions of years. Stars won't actually hit each other. Space is too vast and stars are too small. But the gravitational interactions will be dramatic. Stars will be flung into new orbits. Some will be ejected from the galaxy entirely, cast into the dark between galaxies. New waves of star formation will ignite as gas clouds collide and compress. Our sun, elderly by then and nearing the end of its red giant phase, might be thrown into a different part of the merged galaxy. Or it might be one of the unlucky stars flung into intergalactic space, destined to wander alone through the void for trillions of years. The merged galaxy, Milkomeda, will settle eventually into a large elliptical galaxy. The spiral structure will be gone, smeared out by the collision. But it will be beautiful in its own way. A vast glowing sphere of stars, perhaps 10 times the diameter of the Milky Way. And then, slowly, star formation will wind down. Stars form from gas clouds, but every generation of stars locks up some of that gas in stellar remnants. White dwarfs, neutron stars, black holes. And some gas is expelled from galaxies entirely by supernova explosions and stellar winds. Over tens of billions of years, galaxies run out of gas. The last generation of stars is born, and after that, no more. In about 100 trillion years, 100,000 billion years, the last stars will burn out. The universe will enter the degenerate era, dominated by the slowly cooling remnants of dead stars. White dwarfs, brown dwarfs, neutron stars, objects that no longer generate energy through fusion, just gradually radiating away their residual heat. The galaxies will still exist as structures, but they'll be dark. No starlight, just the faint infrared glow of cooling stellar corpses and the occasional flare when one object collides with another. Life, if it still exists, will have to adapt. Civilizations might cluster around the last remnants of heat, perhaps building Dyson spheres around white dwarfs, carefully extracting every bit of energy as they cool over trillions of years. But even that won't last forever. Over timescales of 10 to the power of 20 years, 100 billion years. Even the structures of galaxies will break down. Close encounters between stellar remnants will occasionally give one object enough energy to escape the galaxy entirely. Slowly, over unimaginable stretches of time, galaxies will evaporate, their constituents drifting alone through the expanding universe. And the expansion continues. Dark energy ensures that. Distant galaxy clusters recede from each other faster and faster. The cosmic web, that beautiful structure of filaments and voids, will tear apart. Each galaxy cluster will become an island universe, forever separated from all others. In the far future, any civilization that exists will see a universe very different from ours. When they look out at the sky, they won't see other galaxies. The expansion will have carried them too far away, their light redshifted into invisibility. Future astronomers will think they live in a small universe containing only their local cluster of galaxies, surrounded by infinite, empty space. They'll have no evidence for the Big Bang, no cosmic microwave background radiation. It will have redshifted into undetectability. They'll have no way of knowing that the universe was once young, hot, and filled with radiation, unless they have records from our era. Unless knowledge is preserved across the eons. Otherwise, they'll have to reinvent cosmology from scratch, with far less evidence than we have. But even galaxy clusters won't last forever. Protons, the building blocks of atomic nuclei, might not be stable. Some theories predict that protons decay with a half-life of about 10 to the power of 34 years. If that's true, then, over timescales of 10 to the power of 40 years, all the matter we know, all the atoms, all the elements, will disintegrate into lighter particles. Electrons, positrons, neutrinos, photons, planets, stellar remnants, even black holes' accretion disks. All will slowly evaporate as their protons decay. The universe will become a thin soup of elementary particles and radiation, growing colder and more diffuse as space expands. But black holes will remain. They don't decay through proton decay. They evaporate through Hawking radiation, but that process is incredibly slow. A black hole with the mass of the Sun will take 10 to the power of 67 years to evaporate. A supermassive black hole might take 10 to the power of 100 years. These numbers are so large they lose meaning. They're longer than the current age of the universe by a factor of billions of billions of billions. But time is patient. Time always wins. Eventually, even the longest-lived black holes will evaporate. They'll shrink slowly, then more rapidly as they get smaller, finally disappearing in a brief flash of radiation. And then there will be nothing left. Just a vast, cold, empty universe expanding forever. Photons, neutrinos, and other particles spread so thin that they might go trillions of light years without encountering another particle. The temperature of space will approach absolute zero. This is the heat death of the universe. maximum entropy, thermal equilibrium, a state where nothing can happen anymore because there are no energy gradients left to drive processes. Some physicists find this depressing. All that beauty, all that complexity, all those galaxies and stars and perhaps civilizations, all of it ending in cold, dark, eternal stillness. But others see it differently. The heat death is trillions upon trillions of years away. The era we live in now, the stelliferous era, the age of stars, might be only the tiniest fraction of cosmic history. But it's the most interesting fraction. The period where the universe is complex, dynamic, alive. We're living in the universe's youth, in its prime. In the brief window when stars shine and planets form and life can exist. That makes our time precious. Not because what comes after is meaningless, but because what we have now is rare, temporary, a fleeting moment of complexity in an eternity of simplicity. And there's beauty in that. The universe won't always be this way. Stars won't always light up the night. Galaxies won't always spiral through space. This is a special time, and we're here to witness it. Moreover, the far future isn't necessarily empty of possibility. Some physicists speculate about exotic forms of life that might exist in the degenerate era or even beyond. Civilizations, operating on timescales trillions of times slower than ours, thinking thoughts that take millennia, existing in conditions we can barely imagine. Others propose that the universe might undergo quantum fluctuations, even in its heat-death state. Rare, random fluctuations might spontaneously create pockets of low entropy, brief islands of complexity in an ocean of uniformity. Perhaps even new universes budding off from the old one. And if cosmic inflation is eternal, as some models suggest, then new universes are being born all the time, far beyond our cosmic horizon. Our universe might fade into heat death, but the multiverse continues, eternally creating new Big Bangs, new cosmic histories. These ideas are speculative. We don't know what the far future holds, but we can imagine. We can extrapolate from what we know and peer into the deep time ahead. And what we see is this: change is inevitable. Nothing lasts forever. Not stars, not galaxies, not even matter itself. The universe is in constant transformation, moving from one state to another, driven by the laws of physics and the arrow of time. But that's not a reason for despair. It's a reminder to appreciate what we have while we have it. To look up at the stars while they still shine. To marvel at galaxies while they still spiral. To explore the universe while it's still young and full of light. Because someday, in the inconceivable future, the last star will flicker and die. The last black hole will evaporate, and the universe will grow dark and still. But that day is so far away, it might as well be infinite. For now, the universe is alive. Complex, beautiful, full of mystery and possibility. And we're here to see it. That's the gift of living in the stelliferous era. We exist at a time when the cosmos is at its most magnificent, when light and matter and energy dance together in patterns of staggering complexity. This won't last forever, but forever is a long time, and we have now. So let's use it wisely. Let's explore while we can. Let's understand while there's still something to understand. Let's reach for the stars while they're still there to reach for. The deep future is patient. It will wait, but the present won't. This moment, the age of stars, the era of galaxies, the time when conscious beings can wonder about the universe, this is fleeting, and it's ours. For all we've learned, for all the mysteries we've unraveled, the universe still holds its secrets close. Science has given us extraordinary insights. We know how stars form and die. We know the age of the universe to within a few tens of millions of years. We've detected ripples in space-time itself. We've photographed the shadow of a black hole. But for every question we've answered, new questions emerge. And some of the oldest, deepest questions remain unsolved. What is dark matter? We know it's there, we can measure its gravitational effects, but we don't know what it's made of. Exotic particles? A flaw in our understanding of gravity? Something else entirely? What is dark energy? We know it's causing the universe's expansion to accelerate, but we don't know why. Is it a property of space itself? A cosmological constant, as Einstein imagined? Is it a new field, a quintessence that permeates the universe? Is it a sign that general relativity needs to be modified at cosmic scales? What happened before the Big Bang? Was there a before? Does the question even make sense? Could the universe have emerged from a quantum fluctuation, from a collision of higher dimensional brains, from a previous contracting universe? Or is time itself a feature that only emerged at the Big Bang, making before a meaningless concept? Why does the universe have the physical laws it does? Why 3 spatial dimensions and 1 time dimension? Why these particular forces and particles? Why these specific constants of nature? Is there some deeper principle that requires the laws to be this way? Or is it arbitrary? Perhaps just one random selection from the string theory landscape? Why is there something rather than nothing? This is the ultimate question. Why does the universe exist at all? Why is there matter, energy, space, time, laws of physics? Why is there anything? Physics can tell us how the universe works, but it struggles with why. Maybe why is the wrong question. Maybe the universe doesn't need a reason to exist. It just does. Or maybe there is a reason, but it's so far beyond our current understanding that we can't even formulate the question properly. Maybe we're like medieval philosophers trying to understand quantum mechanics. The concepts don't exist yet. The language hasn't been invented. We also don't understand consciousness. How does subjective experience arise from physical processes in the brain? How do neurons firing create the feeling of seeing red, of tasting coffee, of experiencing the flow of time? This is the hard problem of consciousness. And despite decades of neuroscience research, we're nowhere near solving it. Some philosophers argue consciousness is fundamental, like space and time, not reducible to anything simpler. Others insist it must be explainable in physical terms. We just haven't figured out how yet. The debate continues. And here's a related mystery. Why does consciousness exist at all? From an evolutionary perspective, we can understand why brains that process information survive better than those that don't. But why does processing information feel like anything? Why is there subjective experience attached to it? Couldn't evolution have produced zombies? Beings that behave exactly like conscious humans but have no inner experience? If consciousness serves no function that unconscious information processing couldn't serve, why does it exist? Some researchers suggest consciousness does serve a function, perhaps integrating information, perhaps enabling flexible behavior, perhaps something else. But we don't know for sure, and the fact that we don't know suggests we're missing something fundamental about the nature of mind and matter. We don't fully understand quantum mechanics. We can use it. It's the most precisely tested theory in all of science. But we don't agree on what it means. Does the wave function represent reality or just our knowledge? Do measurements cause collapse, or do universes branch? Is there hidden structure beneath the quantum formalism, or is reality fundamentally probabilistic? 9 decades after quantum mechanics was formulated, these questions remain open. And then there are the strange features of quantum mechanics that still puzzle us. Entanglement, the phenomenon where two particles can be correlated in ways that seem to violate locality, where measuring one instantaneously affects the other regardless of distance. Einstein called it spooky action at a distance and never fully accepted it. But it's real. We've tested it. Entangled particles really do exhibit correlations that can't be explained by classical physics. We use it for quantum computing and quantum cryptography, but we still don't understand what it means about the nature of reality. Does information really travel faster than light? No. You can't use entanglement to send messages. But something is happening. Some kind of non-local connection exists between entangled particles. The universe isn't made of separate, independent pieces. It's interconnected in ways we're only beginning to grasp. We don't have a theory of quantum gravity. General relativity and quantum mechanics are both spectacularly successful in their domains, but they contradict each other. We need a unified theory that merges them, that can describe what happens at the Planck scale, inside black holes, at the Big Bang singularity. String theory is one candidate. Loop quantum gravity is another. There are others still, but none have been confirmed experimentally. We lack the data to distinguish between them, and we might lack that data for a long time because the energy scales where quantum gravity becomes important are so extreme we can't recreate them in laboratories. We might have to wait for cosmological observations to guide us. Imprints in the cosmic microwave background, subtle features in gravitational waves, observations of the early universe from future telescopes. Slowly, piece by piece, nature might reveal the answer. Or we might need a conceptual breakthrough, a completely new way of thinking about space, time, and matter that makes the answer obvious in hindsight. Like how Einstein's insight about the constancy of light speed led to special relativity, overturning centuries of assumptions. These breakthroughs are rare. They require genius, yes, but also luck. Being in the right place at the right time, asking the right question, having the right background to recognize the significance of an anomaly. Then there's the mystery of cosmic coincidences. Why do the fundamental constants of nature have the values they do? Why is the strength of gravity so much weaker than the other forces? Why is the cosmological constant, the value of dark energy, so incredibly small yet not exactly zero? These constants appear fine-tuned for life. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If the strong nuclear force were slightly weaker, atoms beyond hydrogen couldn't form. If the cosmological constant were much larger, the universe would have expanded too rapidly for galaxies to form. The values seem precisely calibrated to allow complex structures, stars, planets, life, to exist. Why? One answer is the anthropic principle. We observe these values because if they were different, we wouldn't exist to observe them. This is true but unsatisfying. It's like saying we live on Earth because it's habitable, which is true but doesn't explain why habitable planets exist at all. Another answer is the multiverse. If countless universes exist with different constants, we naturally find ourselves in one where the constants allow life. This shifts the question, but doesn't eliminate it. Why does the multiverse exist? Why does it produce different constants in different regions? Perhaps there's a deeper theory that predicts these values. A theory that shows why the constants must be what they are, that there's only one mathematically consistent way for the universe to exist. But we haven't found that theory yet. Science is not a steady march toward complete knowledge. It's a winding path full of dead ends and detours. Sometimes progress comes quickly. Sometimes we're stuck for decades waiting for a new idea or a new technology to break the logjam. And there might be questions we can never answer. Not because we lack intelligence or resources, but because they're fundamentally beyond our reach. If the multiverse exists, we might never be able to observe other universes. If consciousness is truly fundamental, we might never reduce it to simpler terms. If quantum mechanics is irreducibly probabilistic, we might never find the hidden variables we're looking for. There are also questions about the nature of mathematics itself. Why does mathematics describe the universe so perfectly? Is math discovered or invented? Does it exist independently of human minds? Or is it a construct we create? Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences. Equations written by mathematicians for purely abstract reasons turn out to describe physical reality with stunning accuracy. How is this possible? Some say mathematics is the language of nature, that reality is fundamentally mathematical. Others say our brains evolved to recognize patterns, and mathematics is just formalized pattern recognition. The debate remains unresolved. And what about infinity? Does it exist in nature or only in mathematics? Are there infinitely many universes? Infinitely many galaxies? Can space be infinitely divided? Or does everything come in discrete units at some fundamental scale? Physics uses infinity constantly. Infinite space-time, infinite possibilities in quantum mechanics, infinite values at singularities. But maybe infinity is just a mathematical convenience, a shorthand for very large or unbounded. Maybe nature abhors actual infinity. Or maybe not. Maybe the universe really is infinite. Maybe there really are infinitely many stars, infinitely many planets, infinitely many copies of you reading infinitely many versions of this sentence. The math allows it. Nature might too. There might be limits to human knowledge, walls we can approach but never cross. And that's okay. It doesn't diminish what we've achieved. It just means the universe is deeper than we are. But here's the thing. We don't know where the limits are until we reach them. And we haven't reached them yet. Every generation thinks it's close to complete understanding. In the late 1800s, physicists thought they'd solved all the fundamental problems. Then came relativity and quantum mechanics, and the whole edifice had to be rebuilt. We might be in a similar position now. We think we have a good grasp of how the universe works. And then a new discovery will come along. Maybe from the James Webb Space Telescope, maybe from a particle accelerator, maybe from a gravitational wave detector. And we'll realize we've been missing something crucial. That's the nature of science. It's never finished. It's an ongoing conversation with nature, and nature is under no obligation to make itself easy to understand. But the conversation is worth having. Because even if we never reach complete answers, even if there are always more mysteries beyond the ones we solve, the act of questioning is itself meaningful. We are creatures who ask why. It's part of what makes us human. And as long as we keep asking, as long as we keep pushing at the boundaries of the known, we're fulfilling something essential about what we are. The universe doesn't owe us explanations. It doesn't care if we understand it, but we care. And that's enough. There will always be questions. There will always be mysteries, and that's what makes existence interesting. If we knew everything, what would be left to discover? What would be left to wonder about? The unanswered questions aren't a failure. They're an invitation. They're the universe saying, there's more here. Keep looking, keep thinking, keep exploring, and we will. Because we're human. And humans don't stop at the edge of the known. We lean over the edge and peer into the darkness beyond. Sometimes we fall. Sometimes we discover something new. But we never stop looking. And so, we come back. Back from the Big Bang, from the first stars, from black holes and dark matter. Back from the far future and distant galaxies. Back from questions about time and consciousness and meaning. Back to here, to now, to this moment, wherever you are as you listen to these words. Look up if you can. If it's night, if the sky is clear. The stars you see are real. Not metaphors, not abstractions. Real nuclear furnaces burning millions of miles away, separated from you by distances that make the mind stagger. The light entering your eyes left those stars years ago, decades ago, centuries ago. You're seeing the past. You're looking backward through time every time you look at the sky. And those stars are looking at you too. Or they would be, if they had eyes. The light from our sun is spreading outward right now, carrying information about Earth into the cosmos. Any civilization within 4 light years could, in principle, see sunlight reflected off our planet right now from 4 years ago. Any civilization within 100 light years could detect our radio transmissions, our television broadcasts, the electromagnetic noise of our civilization. We are not isolated. We're woven into the universe, connected to it by light, by gravity, by the atoms we share, by the laws that govern us all. For a few minutes, maybe an hour, we've journeyed together through the cosmos. We've explored its strangest facts, its deepest mysteries. We've stood at the edge of understanding and peered into the unknown. We've watched the universe being born in a burst of light and energy. We've seen the first stars ignite in an ocean of darkness. We've followed matter as it organized itself into galaxies, into vast cosmic structures spanning billions of light years. We've confronted the invisible universe, the dark matter and dark energy that make up most of reality. We've approached black holes, those places where space-time itself tears and the laws of physics struggle to apply. We've questioned the nature of time, wondered about other universes, and asked the ancient question, are we alone? We've looked into the deep future and seen the eventual fate of stars, galaxies, and perhaps the universe itself. And we've acknowledged the vast territories that remain unmapped, the questions we cannot yet answer, the mysteries that may forever lie beyond our grasp. But the journey doesn't end here. It can't, because the universe is still unfolding, still expanding, still creating new stars, new galaxies, new structures, still evolving toward whatever future awaits it. And you are part of that future. Think about that for a moment. You, yes, you specifically, are part of an unbroken chain that stretches back to the Big Bang. Every atom in your body has a history spanning billions of years. The hydrogen in your cells was forged in the first 3 minutes after the Big Bang. The heavier elements were created in stellar cores and scattered by supernova. Your atoms have been part of countless different structures over cosmic time. They've drifted through interstellar space. They've been part of gas clouds, of asteroids, of ancient seas on the young Earth. They've been part of bacteria, of ancient forests, of dinosaurs, of other humans. And now, they're arranged in this particular pattern, the pattern that is you, the pattern that's reading these words, thinking these thoughts, experiencing this moment. This arrangement won't last. Eventually, your atoms will scatter again, becoming part of other things, other patterns. But right now, in this moment, they're you. And that's extraordinary. Every breath you take contains atoms that were once inside stars. Every thought you think is a pattern of electrons moving through neural pathways, following the same laws that govern the motion of planets and galaxies. You are not separate from the cosmos. You are the cosmos, experiencing itself. And that experience matters, not because some cosmic judge has declared it matters, but because you're here. You exist. You think, you feel, you wonder. And in wondering, you touch something profound. The universe is vast. It is ancient. It is mostly empty and mostly dark. But here and there, in rare pockets, matter has organized itself into something extraordinary. Into life, into consciousness, into beings who can look up at the stars and understand what they're seeing. You are one of those beings. And that is a privilege, a gift. Not from anyone, not to anyone. Just a fact. A cosmic accident that resulted in you. But it's an accident with meaning, because you give it meaning, because you're capable of appreciation, of awe, of wonder. You can stand beneath the night sky and feel small and significant at the same time. You can contemplate infinity and feel both terror and exhilaration. This is what consciousness brings to the universe. Not just the ability to process information, but the ability to care about it, to find it beautiful, to want to understand it. The universe doesn't need us. It would continue just fine without consciousness, without life, without any witness to its vast unfolding. But we need the universe. It's where we came from. It's what we're made of. It's the only home we have. And maybe, just maybe, the universe is richer for having beings like us in it. Beings who can look at a nebula and see beauty, who can detect gravitational waves and feel excitement, who can discover that space and time are relative and experience the intellectual joy of understanding something profound. We add something to the cosmos. Not much, perhaps. Not in terms of mass or energy or influence at cosmic scales, but in terms of meaning, of understanding, of appreciation. We are the universe's way of knowing itself. And that matters. So what will you do with this gift? Will you look up? Will you wonder? Will you ask questions, even knowing some might never be answered? Will you live as if your existence matters, even if the universe doesn't care? Will you reach out to others, to humanity, to life, to consciousness wherever it appears, and try to build something that lasts? Will you preserve what's precious? This pale blue dot we call home, the biosphere that gave birth to us, the knowledge we've accumulated over generations? Will you explore, create, discover? Will you add your voice to the human conversation about what we are and where we're going? These are choices only you can make. The universe won't make them for you. No cosmic authority will tell you what to do. You have to decide for yourself what matters, what's worth pursuing, how you want to spend your brief time in the sun. But whatever you choose, remember this: you are made of star matter. You are ancient. You are part of a story that began 13.8 billion years ago and will continue for trillions of years more. Your time is brief, but it's real. And while you're here, you have the chance to look up, to see, to understand, to marvel at the fact that you specifically right now, are here to witness this. The universe is full of mysteries. Some we'll solve, some we won't. But all of them are invitations to keep exploring, keep questioning, keep reaching beyond what we know. This is the essence of science. Not just a collection of facts, but a way of being in the world. A willingness to say, I don't know, and mean it. A commitment to following evidence wherever it leads. An openness to surprise, to wonder, to the possibility that reality is always deeper than we imagined. We've come to the end of this journey, but the larger journey, the human journey through the cosmos, is just beginning. We've barely left our planet. We've sent a handful of robots to explore our solar system. We've looked at distant galaxies through telescopes, but we haven't truly gone anywhere yet. The universe is waiting. It doesn't know we're here. It doesn't care. But it's full of wonders we haven't yet discovered, questions we haven't yet asked, stories we haven't yet told. And someday, maybe in your lifetime, maybe in your grandchildren's lifetime, we'll take our next steps outward. We'll walk on Mars. We'll mine asteroids. We'll build habitats in space. We'll send probes to other star systems. Maybe, eventually, we'll meet someone else. Another species looking up at their sky, wondering if they're alone. Or maybe we won't. Maybe we'll remain alone for millennia or forever. But either way, the journey is worth taking, because it's our nature to explore, to wonder, to reach beyond ourselves. We are the inheritors of 13.8 billion years of cosmic evolution. We are the current chapter in a story that's far from finished. And what we do next, how we treat each other, how we treat our planet, how we step into the future, will determine whether that story continues. This is both terrifying and exhilarating. We hold the future in our hands. We always have. But now, for the first time, we're aware of it. So let's choose wisely. Let's choose to survive, to grow, to explore, to keep asking questions, to preserve what's precious and build what's possible. Let's be worthy of the stars we came from. Let's remember that we're connected to each other, to all life on Earth, to the planet itself, to the solar system, to the galaxy, to the universe. We're all made of the same star stuff. We're all part of the same cosmic story. And that story is still being written. Each of us contributes a few words, a few sentences, a paragraph perhaps, if we're lucky. But together, across generations, we're writing something meaningful. A story about consciousness emerging from matter, about intelligence trying to understand the universe it finds itself in. It's a good story, and it's not finished yet. Thank you for joining us on this journey, for taking the time to wonder, for looking up at the infinite and letting yourself feel small and significant at the same time, for being here, in this moment as part of this vast, unfolding cosmic drama. The universe is still here, still unfolding, still full of mysteries, and you're part of it. Not as a passive observer, but as an active participant. You are the universe observing itself, thinking about itself, trying to understand itself. And in that act of understanding, in that moment of wonder, something beautiful happens. The universe becomes conscious of its own beauty. It becomes aware of its own mysteries. It begins to know itself. Through you, through us, through all conscious beings, wherever they may be. This is the greatest gift of existence, not just to be, but to know that we are. Not just to exist, but to wonder about existence. We stand on a tiny planet looking out at infinity, and infinity looks back through our eyes. This has been Infinite Science. And remember, you are star stuff. You are ancient, you are connected, and you matter.